All right, how's everyone feeling today? Any questions, thoughts, concerns before we get started? Okay, well, before we continue with momentum and collisions, want to make sure that you guys are aware of upcoming calendar events for this particular course. The tentative test dates listed in the syllabus indicate that our first test is coming up within this highlighted span of days. That test will be on chapters 1 through 7, so we've still got a little bit more learning to do. We're kind of wrapping up chapter 6 now, and then chapter 7 will be what we spend the first couple days of next week on. Now, the way that I do tests in here, I want to make sure that everyone hears this from me, and it's in your brains moving forward, is that on those days, plural, 19th, 20th, 21st, when you are ready to take the test, you will report to this room during lab time. So instead of having lab that week, you will instead come here to take your test. And that way you have 3 hours to take a 1-hour test, so that you don't have to rush in, do it in 50 minutes, and then rush off to another class. And it's just my general test policy. So, normal lab next week. Next week we're still doing normal operations. Week after that, no lab because of the test. Additionally, since test will be during lab, that frees up lectures for review. So, again, kind of the itinerary for the next week or so of lectures. Today, Friday the 9th, we are working on the tail end of what I call chapter 6. That's going to be about momentum and collisions. Today is focusing mostly on the collisions part. Next week, 12th and the 14th, we're going to do chapter 7, which will be about energy. And that's the last new thing we cover before the test. Moving into the 16th, we'll be heading into test review time, where we will spend class time making sure everyone feels comfortable before it, answering questions, going over review materials. I usually post to Brightspace as a test comes up, list of things you should be familiar with, like all the concepts that we've covered that you can kind of use as a checklist while you're studying. Make sure that there's a fully updated formula sheet available for you guys. The one that's there is fine, it's just a little old, so I'm reformatting it. And you should be treating the homework as a practice test, basically, as practice questions for the test. But before a test, I usually post more so that people have more practice if you want it. Just more practice questions, basically. Yes?
Is the homework supposed to act as a study guide, or are you going to give us a separate study?
Homework is basically a study guide, and that's definitely why I post all the answers for it as well. Homework is a study guide, and you should definitely do the homework as you're studying, like as a form of studying, because some of the test questions are ripped straight out of the homework. Yes?
So is that test going to be like some multiple choice and some short answer, or nothing?
I usually do some short answer and some math. I don't do a whole lot of multiple choice, but that's mostly out of habit, I fully admit. I wasn't given multiple choice tests in physics, and so I just tend not to do them, but I need to rethink that policy. But definitely there will be short answer, and when I say short answer, I mean really short, like a sentence or less is what I'm expecting when I write these questions. And I suppose there is technically one multiple choice question absolutely guaranteed, because I will ask you, out of these 5 statements, pick the laws of motion and number them. Like on, was one of the labs that we did, I think. And again, as I said, I'll be posting like an additional practice test that you can work on in addition to all the homework that you should also be doing. Yes?
Will you be in here with us if we have to stay lab, or will it be Dr. Edwards?
I won't be in here, but Dr. Edwards will, and my instructions to him when he is proctoring tests for me is answer students' questions, make sure they understand what's going on. Same as what I do when I'm here. Yeah, whatever day you take the test, please ask questions during the test. You will also have a calculator and a formula sheet, which you're allowed to write on. You're allowed to write on your formula sheet. You will have a formula sheet. That said, I guess the rules for what you shouldn't put on your formula sheet are the laws of motion. I want want to make sure that you can identify those without assistance. And any worked examples. You can have formulas and notes about the formulas, but no like worked out practice problems. Does that make sense? Additionally, normally normally during proper lab, students don't jump between sections because there's only a certain number of seats in the room for actual lab days. But for the tests, I mean, we're in here, we're not in lab, there's more chairs in here. So on these 3 days, I'm way more flexible about people just attending a different day of the week. Say if you have Monday lab, but you have Wednesday afternoon off, you could attend the Wednesday time to take your test. Alternatively, if you just want it over with, you can jump into the Monday one. I leave that for you guys to decide. Also, I'm not in the habit of giving one dedicated bonus question, because if you don't know that one question, then you don't benefit from it. So instead, I just give you more points than you need to get a 100. There's 105 points, you need 100 of them to get a 100. Feel good? All right. And as I said, lecture days as we approach this time will be dedicated to test review. Once we are done with all the material needed for chapter 7 by about the 14th or the 16th, we'll transition into test review time. And lecture on these 2 days will also be more test review, making sure that you guys feel comfortable, looking at any questions you encountered during the homework or your notes, et cetera, et cetera. I think I had another one, but I lost it. Any questions related to any of these announcements before moving on for the day? All right. In that case, let us continue where we left off. Once I update, please. Gotta love basement Wi-Fi. All right. On Wednesday, we began talking about collisions. The thing that happens when one object functionally just runs into the other. In terms of the physics terms of what's going on within a collision. Collisions always have a before state and an after state. The objects are in some sort of condition with some sort of velocity before something happens. And then there's a separate condition some number of seconds later where the collision is done. And what happens during the collision is the two objects involved exert force on each other for a certain amount of time, because if you run into something, there will be an exchange of force. And those forces, acting for a certain amount of time, cause, as we call it, an impulse. Recall, impulse is just change in momentum. So when the objects exert force on each other, based on the amount of time the collision lasts, the objects undergo some form of an impulse. And since the two objects exert the same amount of force on each other, just in opposite directions, the two objects should have equal but opposite impulses. This leads to the general idea that momentum is conserved in collisions. Since the impulses between the two objects are equal, that kind of implies that however much momentum one object loses in the interaction, the other would gain the same amount. If one object's impulse is -5 kilogrammeters per second, then the other objects would have to be +5 kilogrammeters per second, implying again, however much momentum one lost, the other gained the same amount. It's like the momentum just kind of hops from one thing to the other. We summarize this with the physics principle called conservation of momentum. Again, this idea that momentum's not destroyed when things run into each other and change velocities, but that it's just kind of swapping which object possesses it. As an example, let's say you're playing a carnival game. Let's hope it's not rigged. And you just have to throw a ball at a stack of objects trying to knock it over. Before the collision, where's all the momentum in this situation?
In the ball.
In the ball. That's because the ball has some amount of mass and some non-zero initial velocity. It has to be moving after you throw it. Meanwhile, this block stack isn't moving yet. Its velocity is 0, so whatever its mass is, it doesn't have any momentum before the collision. After the collision, the goal is for the blocks to get knocked over, implying that they would have to have some different non-zero final velocity after the crash. So, impact, blocks scatter. The scattered blocks, their final velocity isn't 0, because now they're moving, right? So now those blocks had to have absorbed some momentum from the ball so that they can be moving. But will the ball be moving as fast as it was before impact? No, the ball is likely going to slow down. Once it collides, it has to lose momentum in order to give some to these objects. And that's the conservation part. The same total amount of momentum must exist between the two stages. There's only a certain amount of it. It's like the charge in a battery. And you're just distributing it differently between the two parts. In the first part, the ball has all of it. In the second part, the ball has to share it with the blocks so that the blocks move. But now, since the ball has less of it, it's not going to be moving as fast. Sound familiar? All right. The math for that, the way that we do the math for that, looks like this. Sigma rho initial equals sigma rho final. This says the total initial momentum of the entire system before impact equals the total momentum in the system after impact. Again, sigma is sum of, S-U-M of, all of the momentum added together before, must be equal to all of the momentum after. Let's say the ball is 1 kilogram and its initial velocity is 5 meters per second. And the blocks have a mass of 5 kilograms and an initial velocity of 0. What's the ball's initial momentum? Mass of 1 kilogram, velocity of 5 meters per second, 5. So the ball's initial momentum, just 1 times 5 kilograms per second. Meanwhile, the block stack, as we discussed earlier, has none, because whatever your mass is, if your velocity is 0, you've got no momentum. Be specific here, momentum initial ball, momentum initial blocks. Because the blocks just aren't moving. So right now, the system's total momentum is 5 kilogram-meters per second. Because we've got 5 here and 0 here. And 5 plus 0 is just 5. So right now, 5 plus 0, 5 is the system's total momentum before impact. That's the total amount of momentum that is present in this scenario. And that total amount will remain constant even after impact. So whatever momenta these two things have afterwards will still add up to 5. How do I feel so far? Okay. I've got a different full example prepared that we're going to take a look at now, so we can start applying the way that that formula was written. Let's cause a different sort of collision, one with pre-prepared numbers. We are going to throw a very sharp object at a piece of wood. The idea being that, the object, the throwing star, is going to stick into the wood and embed in it so that it's not bouncing off. We'll talk about what happens in that case later. As I said, every collision has a before state and an after state, so I'm going to sketch out a before picture and an after picture. We are throwing a 100-gram object, and its initial velocity is 25 meters per second. I just went with a throwing star because, again, it'll stick into the wood. Throwing it at a very poorly drawn log. This log has a mass of 16 kilograms, and its initial velocity is 0. It's not moving at first. Logs don't tend to move around on their own. So here's our before state. We've thrown the object, it's moving through the air at this speed, and it's being launched at this target that is not moving. So this is before impact. This is what we know given the numbers listed. I'm calling the star mass 1, and therefore its initial velocity I'm calling v initial 1. I'm just deciding that the star is object number 1. Separately, the log, I've got it listed as object 2, so m2 is 16 kilograms, velocity initial 2 is 0, because it's not moving yet. So that's our before state. Afterwards, as I kind of already said this part, the star is just going to stick into the wood. It will embed in the wood's surface. Now, it's important to note that the mass of the two objects didn't change, because mass does not spontaneously ever change by itself. We still have 100 grams of steel and 16 kilograms of wood. What is going to change about the two objects in this final stage? Yeah, their final velocities are going to be different. Because the star is definitely going to slow down upon hitting the log. And what do you think the log is going to be doing afterwards? Let's just say it was initially sitting still on a fence post. Might tip over. Might have just enough velocity to tip over. Point is, though, that's a different final velocity to either of the initial ones. Star's probably going to slow down a lot. The log might speed up a little. So that final velocity is different for both items. But note though that since they're stuck together, they're probably gonna share this final velocity. Because if your two things are physically stuck, they kind of have to move at the same rate. Like you and your car both move at 70 miles per hour if you're in it. So, that final velocity, that unknown final speed, is the thing we want to know. We want to figure out how fast the log-star combo is going to move right after impact. See if it's enough speed to knock it off of this fence post. And we are going to figure that out using the conservation of momentum. I guess feel about the setup before doing any math. All right. Marker with more ink in it. Need a better filing system. That'll work. So, looking back at the equation I listed a second ago for conservation of momentum, what this says is, however much momentum is in the before stage is the same as the total in the after stage. Just let me rewrite this to be a little more symmetric. So, I'm going to figure out how much momentum is in the before picture, and that'll go here. The same amount of momentum must exist in the after picture. It'll just be distributed differently. Different objects will have different amounts of it. So that's again what the formula says. The total from the two stages must be the same. And there's two objects present in each stage. The star is present on both sides, the log is present on both sides. So we have to account for each of those objects' momentum levels both before and after. On the before side, again, sigma momentum initial, we want to take the two momenta and add them together at their initial levels. So I'm going to write here, instead of sigma momentum initial, I'm going to write out the two different momenta that need to be added. Momentum star initial plus momentum log initial. So whatever their initial levels are here in the before side, added together, and set equal to, both items are still present in the after stage, but they'll have different final momentum levels. So separately from their initial levels, we have to list out their final levels. This is how we start with sigma rho I equals sigma rho F and start expanding it outward based on what objects are present. How do I feel so far? Okay. Now, what is the star's initial momentum level? Remind me, what's the formula for momentum again? Very good. Mass times velocity. Star's mass is 100 grams, and its initial velocity, because again we're on the before side, is 25 meters per second. So now instead of rho star initial, I'm going to write in what that should be equal to. The star's mass times the star's velocity. Now that said, do I want to write 100 grams? What should I write instead? 0.1 kilograms, very good. We can keep the 25 as 25 though, we like meters per second. So that is the star's initial momentum level. It's not going to be a lot. It doesn't take a lot of momentum to get a small piece of metal moving. How about the log? How much momentum does it have to start? 0, very good. It's stationary. Its mass is 16, already in kilograms. We don't have to do anything about that. But its initial velocity is 0. So this now represents the total amount of momentum present before impact. basically the amount that you would put into the star when you throw it. Initial side feeling okay? All right. Now let's look at the final side. After impact, the two masses remain the same. Again, mass does not spontaneously change. It's still 100 grams of steel, 16 kilograms of wood. So the masses from the first side aren't going to be any different, but what is going to be different on this side? Velocity. Yes, it's not a trick, I promise. Both objects are going to have a different final velocity compared to their initial velocity. Star is going to slow down a lot, and the log is going to speed up at least a little bit. So both of the final is different to the two initials. We don't know what that final is yet, so that's still an unknown. We have to leave it as a variable, and we'll solve for it later. But the masses are unchanged. So we've still got 0.1 times the star's final velocity plus 16 times the log's final velocity. Same two masses, just multiplied by the different, currently unknown final velocity. And this is how we tend to set up conservation of momentum collisions, to try to figure out what that final speed is. How do we feel so far? Just checking in. Okay. Now, VF is the only unknown, so we are good to use algebra to solve for it. I want to point out kind of a quirk to this type of collision. Since the two objects are stuck together, they are going to share the same VF. I wrote just VF in both positions here because it's going to be the same final velocity. I didn't write VF1 or VF2 because it's going to be the same. They're stuck together. It has to be the same. That won't always be the case. You should pay attention to what type of collision something's going to have. We'll talk about that in a minute. In this particular question, the type of collision is going to cause them to stick together and share a VF. So that's the same final velocity in two different positions. We're going to take advantage of that. Now, there's no unknowns over here, so we can just use algebra, get a number for the left side. What does your calculator say 0.1 times 25 is?
2.5.
Very good. And what's anything times 0? So the entire left side will ultimately just compress down to 2.5. That's the total amount of momentum within the system. 2.5 kilogram meters per second. That amount stays constant because it has to. The momentum's not destroyed. It's just that a lot of momentum is going to exit the star and enter the log. They're going to now split this 2.2 between themselves. Sorry, 2.5. I misspoke. On the right side, again, we have VF in two places. What property of math can we take advantage of here? Even if you don't know the name, what would you think to do if you're looking at that?
Add them together.
We can't add them together because they have the same unknown variable. We can add them up directly. I'm going to show how that works indirectly by making use of the distributive property, is the word I was fishing for earlier. They both have a VF in them, so I'm going to distribute VF out and leave behind 0.1 plus 16. But that is basically the same as just adding the two terms together. Again, you can only do that if it's the same variable. If it was 2a plus 5b, you can't do that. running out of board, so I'm gonna take this over here. Left side, I'm just gonna shorten to 2.5. Right side is gonna be 16.1 times VF. We can add the two numbers together inside the parentheses we created because neither has a variable left. But whatever they add up to is still multiplied by VF. And what should our last step be? Very good, we'll just divide. So you're gonna wanna pop 2.5 over 16.1 in your calculator, and that final velocity will be very small. Does anyone's calculator disagree with approximately 0.155 meters per second? All right. So this is now the dramatically reduced shared final velocity of the two combined items. Note, from the star's perspective, that's a big drop. Star goes from 25 down to 0.16, basically. Whereas the log increases from 0 to 0.16. So they have the same final, but they started at different initial points. But this is how you can use conservation of momentum to get what you want. One quick thing I want to prove. I'm going to prove that the two objects have equal and opposite impulses real quick. So, impulse star. Star's mass is 0.1 kilograms. The change in the star's velocity, it ends at this. So VF is 0.155, and it started at 25. So this would tell you the star's impulse. Separately from that, the log, 16 kilograms, it ended at 0.155, but it started at 0. Same ending point, two different initial points. And my goal is just to quickly show the impulses should end up being equal and opposite. However much momentum the star loses, the log gains. The star's impulse should be negative 2.485, I'm rounding. And the Woods is positive 2.48. Any small difference there is just accountable for rounding. Equal and opposite impulse. Star loses this much, log gains this much. The total amount of momentum is consistent from start to finish. And therefore, the two objects exert the same amount of force on each other, but their different masses cause very different reactions to the same impulse. How do you feel? All right. Yeah, that just restates what I already said. All right. Now, the conservation of momentum works for all collisions, even if it doesn't look like it does. Momentum is conserved in every collision. The total amount from start to finish must remain the same. If it doesn't look like momentum was conserved, it's probably because one of the objects is either really big or really small. For example, if I drop this golf ball to the ground, where does all of its momentum go? A little louder, please. Into the ground. Why does the ground not suddenly have a velocity that we can measure? Or it's too big. You know, if I put 5 kilogram meters per second of momentum into the planet, it's not going to budge because its mass has 11 zeros on it. So every type of collision, the momentum is conserved. Sometimes the masses are just very unfair, like one is far bigger than the other, and it might not look like it is, but it is. That said, shouldn't have swallowed that ice. There are 2 types of collisions, and I'd like you to at least be familiar with the difference between them. 2 major types. This is one of the things we'll be exploring in lab next week as we actually cause some collisions in a very safe way. The 2 main types of collisions are elastic and inelastic. The example we just did of the star and the log is an example of an inelastic collision. That's because neither item is elastic in nature. Neither the star nor the log are bouncy or springy, and the objects stuck together. The physics definition of elastic is an item that is able to stretch and then go back to normal all by itself. Wood can't do that in this particular case. As the star makes a hole in the wood is not able to spring back to normal all by itself. The wood, the technical term is deforms. The wood deforms in this interaction. Physically, there's now a hole in it. That hole isn't going to fix itself. And so these 2 inelastic, non-rubbery objects, any damage that happens will remain, and nothing springs off from each other. So in this type of collision, the objects tend to stick together afterwards. In an inelastic collision, since the objects aren't bouncy or springy, if they hit, they tend to stick together and share a final velocity. Note again, they have the same VF here because they're stuck. They have to have the same VF. This happens if objects don't bounce, can't stretch, just get crunched on impact and stay that way. The other type of collision is an elastic collision, and these tend to involve objects that are elastic, meaning that if you deform them somehow, they will spontaneously, of their own volition, return to normal. They are springy, basically. If I squeeze this, it will return to its normal shape. So this is an elastic item. And when it collides with something, it tends to bounce off. That's because on impact, it'll squash and then fix itself, kind of kicking back up off the table. Elastic objects bounce off from each other, and as a result, elastic collisions tend to be very high energy, they're very chaotic, and the objects usually don't have the same final velocity. If they spring away from each other, even if they're moving at the same speed, they're moving in different directions. These types of collisions are chaotic, and the 2 objects don't share a VF. That's the key difference that will inform your math. Elastic, different final velocities. Inelastic, the same final velocity. And this ends up kind of affecting where the momentum ends up. The momentum is still conserved, but this will affect how much of it ends up where. I've got one more quick example to try to demonstrate this. Just to demonstrate the difference between the 2 types. I should have erased that part. We're going to take the same basic starting point but treat it one way inelastically and one way elastically, just to demonstrate the difference. We're going to take a 1 kilogram object and throw it at 10 meters per second at a second 1 kilogram object. So M1, 1 kilogram. Velocity 1 initial is 10 meters per second. Being thrown at a second 1 kilogram object, its initial velocity is 0. We're throwing one thing at a second stationary thing. And first we're going to treat this inelastically like we just did with the star on the log, just to kind of show the similarities. If these were inelastic objects, for example, some form of putty or Play-Doh that changes shape on impact and stays that way. Play-Doh doesn't turn back to normal on its own, usually. These objects are probably going to physically stick together. They will go splat. The masses are the same, but now they will have, like the star in the wood, a different combined final velocity. They're now stuck. They have to share a final velocity. And we'll just go through the steps again to determine what that final velocity most likely is. So we have to track the initial momentum of either object and separately the final momentum of either object. Initially, we got 1 kilogram moving at 10 meters per second, so that'll be 1 times 10. Separately, we've got 1 kilogram moving at 0, and so 1 times 0 is just going to be 0. So there's 10 kilogram meters per second of momentum present here. And inelastically, if they are inelastic putty-like objects that are going to stick together and travel as one, those two masses will have a unified final velocity, like in the previous example. So again, same as before, just changing a few numbers. Masses are different, velocities are different. On the initial side, 1 times 10 is 10. Yeah, 1 times 10 is 10, 1 times 0 is 0, so the left side just becomes 10. On the right side, this is basically just VF plus VF, so 2VF. And what would the final velocity of the combined putty blob be in this scenario? 5. Final velocity 5. This kind of implies that object 1 brings 10 units of momentum to the party, and now they're going to split it equally. Does that make sense? They're stuck together, they have to share. They each now have 5, and so 5 plus 5 is still 10. First ball loses 5, the second ball gains 5. This will be slightly different if instead of deformable objects like putty, we are dealing with something like an elastic ball, something that is, I want to make it clear, I just said an space elastic ball, something that is designed to bounce. So over here, we're going to look at a different after state. Same before state, different after state. We've thrown a 1 kilogram object, but instead of putty or Play-Doh, they're going to bounce off of each other. They're still each 1 kilogram. But in this collision, they will strike one another. Object 1 is going to stop dead in its tracks And object 2 is now gonna rocket away at some unknown final velocity. We gotta figure out what that final rate is. This is kind of like those desk toys that are called Newton's cradles, where one ball swings down, strikes the next one, first one comes to a dead stop, and the one at the end now starts moving away. Perfect exchange. So, initial state's the same, because it's the same masses moving at the same initial velocities. So that initial side is still going to be 1 times 10 plus 1 times 0. 10 kilogram meters per second of momentum present initially. But on the final side, we now know one of the final VFs. It's 0. The first one just stops. It's not an unknown anymore. And whatever it is, it's now going to be different to this one. So elastically, different VFs. And we have one of them. It's not an unknown. So there's only one VF now. The other one's 0. And so this will just go away. And that will leave us with, well, VF2 specifically, V2F. And so, in this scenario, the second object's final velocity is 10. This is meant to tell us that in this scenario, where ball 1 comes to a dead stop, it's losing all of its momentum and giving all of it to the second object. Inelastically, they had to share. They're both at 5 meters per second. They both have half of the initial total momentum. But here, object 1 loses everything and gives it to object 2. This is the primary difference between elastic versus inelastic collisions. Inelastically, objects stick together, tend to have the same VF, and the whole situation tends to be less chaotic. There's less acceleration going on here. Ball 1 drops from 10 to 5, ball 2 increases from 0 to 5. That's a delta 5 for either of them. But over there, same total amount of momentum, it's just distributed differently now. Ball 1 loses all of it, gives all of it to ball 2. Ball 1's change in velocity is now negative 10. It loses all 10 meters per second. And then ball 2 gains 10. It goes from 0 up to 10. So even though the momentum totals are the same, the accelerations are different between the two stages, between the two types. And this type of collision ends up being more chaotic for that reason. And there tends to be more force involved. Elastic objects ricochet, they kick off from each other, and though they tend to exert more force on each other. And that is what lab will be about next week, as you cause some collisions and you take some data about them. For right now, how do you guys feel about the definitions of the two types? All right. Again, you should be looking over the homework. Next week, again, we'll be covering energy and then moving into test review territory. So if you need anything or have any questions, please have a wonderful weekend.